This is a demo of Adaptive Computing's HPC Cloud On-Demand Data Center or ODDC product using the Extreme Scale Scientific Software Stack or E4S Pro running on AWS. ODDC provides a web-based interface for managing all aspects of creating a cluster and on a cloud system such as AWS. It helps you to configure a cluster, build a software stack based on the E4S Pro Amazon Machine Image or AMI, and then monitor the jobs, view accounting information, perform administrative tasks, deploy a cluster, and connect to it using a remote desktop session on the head node of a cluster. ODDC is part of Adaptive.ai as a service offering from Adaptive Computing. You may visit their website at adaptivecomputing.com to learn more. The E4S website is e4s.io, and E4S is built using the SPAC package manager, whose website is spac.io. Now, to deploy a cluster on AWS, we first upload our AWS credentials in the credentials manager of ODDC, and then build a stack based on the E4S AMI. We can view the instance prices and see what each instance costs in different AWS regions. And then we can deploy the image that we have built using the cluster manager of ODDC. And it gives the organization the ability to leverage cloud service provider resources without vendor lock-in to any single CSP. ODDC with E4S provides support for multiple cloud providers using the same consistent user interface based on VNC running on the head node. Instead of manually editing YAML files for cluster configuration and installing tools from the cloud service provider on your desktop, we can use a web-based interface for all aspects of managing the cluster using ODDC. We can deploy a remote desktop session based on VNC on the cluster running our E4S Pro image on AWS. And to do that, I can click on this configuration tab and then click on the view VNC, open VNC viewer. And with this, we will get a session like this, where we can connect to it and send our credentials. The first time it sets up the terminal window, it opens up and installs the SPAC package manager in the user area as well. It's copying the examples. And now this is set up. So we have two compute nodes and a host login node. So there are many packages that are installed in this distribution. And E4S includes over 100 HPC and AI/ML tools installed using the SPAC package manager. SPAC find-x will show me the top-level specs of these over 100 packages that are installed. These include tools like Tau, Trilinos, PETSc, Sundials, HDF5. There are a number of other packages that support this installation, and you can see that we have over 700 packages installed on this particular instance. There are generative AI tools. There are packages such as OpenAI that are pre-installed. So you can say Python and say import OpenAI, and it will be available. So let's just look at an example of using a generative AI example with OpenAI. Now you can go to openai.com, set up a login, and then download the secret key. Here I have a key that I have downloaded, and I can then bring in any generative AI app. So here is a simple chatbot that I've written. Let me just cut and paste this. And to do that, I will use this Command C, and I'll open up this, and let me just paste over here. And if I open up a file, I can just paste this. Okay. Let me just change the permissions so I can launch it as an app. And then I can set an environment variable called export OpenAI API key and cat my ParaTools key that I had downloaded from my account. So with this, I'm now set up to run this quest.py example. So I can say /quest.py, and it will create this ParaTools chatbot for me. And it says, what is your quest? And I can say, let's look at a programming task. Let's say multiply two 512 by 512 matrices with random numbers using C. So I'll ask it to generate code for this. Let me just go to an OpenAI directory and wait for a response from this chatbot and generate a simple example that multiplies two matrices. And here is the example. It says this code generates two 512 by 512 matrices filled with random numbers ranging from 0 to 9. It performs matrix multiplication by iterating over rows and columns. And here is the multiplication. And then it prints out the values. There may be too many values to print out. So let me just go and open up a file called, say, foo.c. Put this in here. And maybe I don't want to print everything. So let me just comment out this print loop and maybe just print f %d and then put in some result, maybe 4 and 6, just one element, and return. Now I can say gcc foo.c foo-o3 and say run this. And I get the result. Now I can change this code because we are in this chatbot session. So I could say, would you please use would you please allocate arrays on the heap and use 2048 as the size of the matrix. Okay. It will generate this code. Instead of using arrays that are in the stack, it will use heap. So we are continuing this conversation. It will refine this code, and let's see how we can do. I see it's multiplying these two matrices using the for loop I, then j, and then k. And now it has created this using malloc on the heap. So you see the free statements and the print, and there it is. This is the code. I can say f1.c, copy this code. Again, let me just comment out this and print just one element. Result, say 4 and 6. And I can say gcc f1.c f1-o3 and f1 time f1. And it will run this 2K by 2K program. Now I can look at this and see what is it doing. it's setting these random numbers, and then it is multiplying them using I, J, and K. And this took 26 seconds. Now I can tell it some advanced queries. I could say, would you please interchange the loops for better cache efficiency? And let's see what it does to this IJK loop in this matrix, which is taking about 26 seconds with O3 optimization. And then this chatbot will respond with a different program. So let me just open up a file. And it says, in this updated code, the order of loops for multiplying matrix 1 and 2 have been interchanged. Now, instead of IJK, you can see that this helps improve the cache efficiency by accessing the arrays in a more cache-friendly manner. It's doing IK and then J over here. So if I take this result and use it, again, let me just print out only one element instead of all of these and say 4 and 6. And I say GCC f2.c, giving me f2. Look at O3 optimization. And let me time this and compare it with f1 for the same code. And instead of 26.191 seconds, it took just 4.5 seconds because it was accessing the arrays in a more cache-friendly manner. And so here, I can see that we sped it up significantly by just asking the right questions. And even the O3 optimization did not help in this case. But it could reorder the loops of this computation. So generative AI provides a very interesting set of opportunities for us to write programs collaboratively with this chatbot. We have many other Python packages that are included in this distribution. Let me show you, besides this OpenAI, we have, say, PyTorch, TensorFlow, we have JAX, we have these Python codes that can all be accessed with the Jupyter notebook. So in this case, we're just looking at here, import torch worked. I can say JAX. I can say import NumPy, import SciPy, import CV2 for OpenCV, and I can import Keras, sklearn for scikit-learn, and most commonly used tools in Python are also here. Import pandas, import matplotlib. And in case we don't have a particular package, let's see how we can install that. So for instance, if I wanted to pick another package and say openram.org is a Python toolkit, which is an open source static random access memory compiler. Now, if this is a package that's not available, as in if I say openram and it says it's not there, then how do you install such a tool? You can simply say pip3 install -- user open RAM, and then it will install this tool in your application. And I can say Python import open RAM. It's there, along with other toolkits such as TensorFlow. So we have a number of these tools that are all available for our AI/ML workflows. Let's have a look at, say, a simple example, JAX, simple neural net, and it's running this code for training. And I can simply say Python JAX this, and it will run this application. Now, this is a setup which includes the login node as well as compute nodes. And we have here, this is downloading the data set and it's running the application. And there it is. We can have multiple terminals here. And you can see the training data set. So to access all of these packages in the Jupyter notebook, I can simply say Jupyter notebook and launch this. It will launch the web browser, and then we can run this in the web browser. Here is the output of the JAX application. And let me just create a new notebook like this. I have this OpenAI session open. I could say, show me an example of, say, matplotlib using colors and lines. And we'll just access the matplotlib Python package through this Jupyter notebook. Now it's thinking, it will generate this matplotlib example that I'll copy and put over here. So here is the matplotlib example that the chatbot generated. And then I'll just go here, I'll post it and put Shift Enter. And there it is, colors and lines, and you can see the code for generating this. So all of these Python packages are now available through the web interface of Jupyter Notebook. And I can ask it many different questions about programming. And let me just leave this page. So we have a head node, and I can say host name, and I can see this is E4S. And then we have compute nodes. There are two compute nodes that are allocated here. Let me just look at MPI and look at MPI proc name. Simple example, MPI proc name.c. All I'm doing is including the MPI.h header, doing an MPI in it, MPI finalize, look at the communicator size and rank, and then get the processor name, the compute node names, and show you that I'm such and such processor out of so many. To compile this, I can say compile.sh, and I use the MPICC compiler. And then I can just run ODDC.sh. I launch this with MPI run, and it's running on two nodes, on the nodes compute nodes 0 and 1. There are two distinct nodes, and here is the run ODDC.sh, where it then creates a host file called hosts.txt that includes the names of the hosts. So with this hosts file, we can launch other tasks, such as here is the OSU benchmark. Now, we have allocated two nodes on AWS. these two nodes are connected by the elastic fabric adapter. The elastic fabric adapter has a peak bandwidth of 50 Gbps. So let's look at the latency and look at the bandwidth of this and see how close are we to the 50 gigabits per second mark. So I can say sbatch, or rather run ODDC latency.sh, because I'm using MPI run with a torque-based scheduler from this ODDC environment. So I can say run ODDC latency.sh, and then it uses this hosts file in the host file parameter. And it is showing me that it has a latency of 21.89 microseconds between the two nodes for these small messages. Now, this is because the two nodes are put in a cluster placement group. So they are close to each other, and we get good performance with this placement group. Let's look at the run ODDC bandwidth.sh. And here I say run ODDC bw.sh. And I see a number which is 6051.56 megabytes per second as the peak value. So in megabits per second, it is this number, or in gigabits per second, it is like 48.4 gigabits per second, roughly. So we are getting 48.4 out of 50 gigabits per second because of the placement group. And one of the important things when configuring MPI is that it must use the libraries efficiently. It should use the libefa library and not the OFI layer, but the actual elastic fabric adapter layer. So if I look at the which OSU bandwidth, I can see that it's using this libefa.so directly. Within the node, also MPI has some important considerations, like xpmem is used. So if I ask the chatbot, what is xpmem, it will tell me what this library is and what it does. When you configure a cluster, it's an important consideration to make sure. So it says xpmem, short for cross-partition memory, is a Linux kernel-based inter-process communication mechanism that allows for shared memory communication between processes running on different nodes of a shared memory multiprocessor system. So this is important in HPC environments. It allows us to get a unified virtual address space so that we have efficient communication between MPI tasks running on the same node. So I could ask it, say, how can I tell if it is installed on my system? And it will look at this and say, it says open a terminal. You can look at this and look at the config and see the LD config and grep xpmem. You can check for the xpmem library, verify kernel support, and look at this. So I have xpmem present over here on the system. I can say, how can I tell if my MPI library is using it? And let's see what the chatbot responds. So I have my MPI installed over here. And in this directory, it is saying that you can check with XPMem whether your library is installed with using it. But we are using MVAPICH. So check the library that you're using, and then we can then evaluate that. How can I tell my MPI library has XPMem symbols in it? And where is my MPI library? It is located over here. So it's saying, look at this library and then see if it has symbols in it by looking at the NM output. So I can look at this library, and I'm seeing lib64 lib mpi.so. I can say nm-d on this library and maybe grep for xpmem, and there it is. So our MPI library is built using this xpmem internally. I can quit from here in the OpenAI examples. There are many other libraries that are installed over here. And let's have a look at some examples of applications. Here is examples directory with demo. Is a tau demo, and I have paraprof, a visualizer for the performance data. Tau is a profiling and tracing toolkit that can show you the performance of your application, and you can then see the performance of your codes. Let me just change the preferences and increase the font size slightly. Use bold. And I can see the time spent in different routines on that particular node, comparing two different nodes like that. I can look at the 3D graphics provided by this. And here I can see the MPI ranks. I look at a bar plot, MPI ranks, the function names, and the time spent in different routines like this. With a crosshair, I can zoom in and see the value of a particular thread of execution and see exactly how much time is being spent in different code regions. So on this loop in rank 199, it took 129 seconds. And you can see that these two functions are kind of inverse of each other. There is a scatter plot that shows you the time spent in a particular rank from 31 seconds to 260 seconds for MPI barrier. And all the MPI ranks have a unique value for the three functions that are plotted here. There is a fourth color function, which has a color scale over here. You can see the time spent is anywhere from 103 seconds to 296 seconds. And one CPU is doing something different from all the rest. And these two functions are kind of inversely correlated with each other. So you can see the graphics. This is just one example of a GUI that's running here. We have other examples. Here is ParaView, a state-of-the-art visualizer. And it's looking at the results of a simulation that we did. I can open up this eye and then apply this. And I have a 3D visualizer here. Let me expand this. Let me change this to turbulent viscosity, surface to surface with edges, zoom in. And this is a CFD fluid flow over a plate application from Nalu Wind, a wind turbine simulation code from Sandia National Labs and National Renewable Energy Labs. And I can look at, say, the pressure and press play, and you can see the pressure during the simulation. So this is just one example of the kinds of things we can do with this visualizer. And it's all running on the cloud on AWS. The performance is pretty good. There are other examples too that ship with this. If you want to see here's another canned example. I can click on this and say here, loading this, and this is a 3D visualizer. And it's very responsive as a GUI application. We also have other tools for visualization, including Visit from Lawrence Livermore National Labs. I have a Visit visualizer here. And I'll load this file, example.silo, in it when it comes up. ParaView and Visit are often used in the HPC community. And there, it's loading up. So let me just dismiss this and say file, open file, example.silo, and add, say, a pseudo color. Add a pseudo color of, say, pressure, and click the draw. And then here is the 3D window. I can say, take an operator, slice it, iso surface, and draw it, and you can see the visualization. So with this remote desktop environment based on VNC, we can have a head node of a cluster that can be used for analyzing the data that's generated from our simulations based on HPC and AIML libraries. And we have a number of different packages. As I mentioned, here are examples of libraries. We have, say, SuperLU dist, we have PETSc, and here is an example of PETSc running on the CPU. Here is clean.sh, clean.sh. Here is a compile.sh file. And all I'm doing is saying, what is the location of this library? And looking at PETSc library. So I can say stack find PETSc. And you can see that. And I can say compile.sh. And there it is. It compiles it. creates the EX50 and all the packages that it needs. So if I say spac find -dl-v PETSc, it will show me the dependency listing and the variants of PETSc. And you can see that here is the PETSc. It's using other packages like HDF5, like Metis, MVAPICH 2x, Parmedis, Python, SuperLU dist, and I can say run oddc.sh. I can say run oddc.sh, and it will run this on, run oddc.sh, and it will run this on the two nodes. And there is the output. There is SuperLU dist. Similarly, I can say compile.sh, compile.sh, and then run oddc.sh, and it will run this. So you can have a look at the codes that are available, all of these 700 plus packages, which support the high-level specs. And there are some interesting other packages here too, like in this demo. I have Julia. Let me show you run.sh. Is which Julia. You can say run.sh. And here is the Mandelbrot set that it created from Mandelbrot.jl file. And you can see the output of this. We also have Rust installed here besides Julia and Python. And you can, let me just go back to our chatbot and say, what is the difference between Rust and C? So in the Rust programming language, what are the key features that differentiate it? I can say spac load Rust. And it's saying memory safety is a big one. Concurrency and safety, static typing, ecosystem and community. I could say, show me a simple example of using Rust. And it'll say, here is a simple example. And I should put it in a file called hello world.rs. And I can just put this in here, print hello world, and say Rust C hello world.rs. Hello world. And there it is. You can ask any of these complex queries. Say, what are the advantages of, say, using AWS? And it's saying the advantages of Amazon Web Services include scalability, flexibility, reliability and availability, security, cost-effective, global infrastructure, ecosystem and integration. What is so special about EFA on AWS? And it will tell us something about the Elastic Fabric adapter. And it's saying it has low latency and high bandwidth, the Elastic Fabric adapter for communication intensive workloads on AWS. And here are some of the advantages for using that. What is adaptive computing? ODDC. And let's see if it on-demand data center. And we can see that at the adaptive computing here. Some key features of adaptive computing's ODDC are virtual infrastructure, scalability, self-service provisioning, multi-tenancy, pay-as-you-go model, high availability, and disaster recovery. You can learn more about it at adaptivecomputing.com. And they can create different instances and different customized solutions using the E4S stack, and then launch the image on one or more cloud providers using the same interface that we just saw. So you could get the same operating system, same interface across different cloud providers using the adaptive computing's ODDC product. So please reach out if you have any questions.